Hello, honors physics students. Let's start with problem number 5 in your projectile motion practice problems. I know it seems a little bit strange why we're now just starting with number 2. That's the one we left off with. But this one is a full and complete problem, so I think it's going to go through all the aspects of a horizontally launched projectile that we need to do. So go ahead and read letter A, and like it says to right there in the space provided, go ahead and sketch out a picture of what's happening. Okay, your picture doesn't have to look exactly like mine, but I drew something like this, right? Using the drawing tools, some sort of level ground. We got a cliff going on there, and there's a picture of a cannon shooting out a cannonball. Mine's gonna be shot out to the right. However, if you have yours shot out to the left, that's absolutely fine. You don't have to change anything about what you've done. Just everything's gonna be sort of flipped in the sort of the direction, but that's absolutely fine. It does say to label the given information, and it says it's being launched at 70.7 meters per second, purely horizontally. Okay, so we're going to label it like so. Now notice I'm calling it V sub L. L in this case stands for launch. You might have called it V naught because it is certainly the initial speed that's being launched at, but that's going to get a little bit confusing as we start to set up our chart because we're going to have V naught on the vertical side. We will also have V naught on the horizontal side, and I don't want to confuse the issue. So we're going to call it V sub L for the launch velocity. We know that the cannon is 34 meters off the ground, so I'll label that on the picture as well. And then it says to draw the path of the cannonball, so if you haven't done that yet, go ahead and do it. And remember, it's not just any sort of curved trajectory, it's going to be a parabolic trajectory. It's not like the cannonball goes straight for a while and then falls. That's only what happens in cartoons, right? When the character all of a sudden realizes there's nothing underneath them. No. In reality, the cannonball starts to fall as soon as it leaves the cannon, and so it's going to follow some sort of path like this. So there's its parabolic trajectory. Okay, so at this point, if you have some experience doing projectile problems, if you want to go ahead and start setting up the chart and solving the problem, that's fine. But more than likely, this being only the second time we're doing this as a class, maybe you want to follow along with me doing it here and then pause the video when I tell you to. So we have our vertical versus horizontal chart set up, and one of the first things we want to do is establish positive directions, just like we had done when we did it in the notes on the grid in class. All right, so the cannonball is clearly falling down, so we're going to call down the positive. I think that makes the most sense. And it's being shot to the right, so I'm going to call right positive. Obviously, if you have the cannonball going to the left, you're going to call left positive, and that's absolutely fine. Nothing's going to change about your solution. But we have two different dimensions of motion, we should have two different positive directions. And then we're going to start to label all the information we know, specifically the initial velocities and the acceleration. So if you want to pause the video here, and on the vertical side and the horizontal side, list what V naught is equal to, and list what the acceleration is. This is a purely horizontal launch, which means when it's coming out of the cannon, it's not going up or down. So the initial vertical velocity is going to be 0. For the horizontal, well, that's what the 70.7 meters per second is. So I write V naught equals 70.7. And I also talk about the accelerations. Remember, the whole idea is that a projectile problem is really just an object in free fall. As soon as the cannonball leaves the cannon, it's already in free fall, and so the vertical acceleration we know is going to be 9.8 meters per second squared, the acceleration due to gravity. But is it positive or negative? Well, let's remind ourselves, of course, it's accelerating down, and we call down the positive direction. If they agree, of course, it's going to be a positive 9.8 meters per second squared. What about on the horizontal side? Well, now we bring the forces into play. Once the cannonball leaves the cannon, the only force acting on it is gravity, and that's a vertical force. And since there's no other forces, there's no other sort of acceleration, right? And so with no horizontal forces, there's no horizontal acceleration. This is going to happen every single time we do a projectile problem. The horizontal acceleration will be 0 because there's no horizontal forces. Now, before we move on, let's remind ourselves what this means. If the horizontal acceleration is 0, that means the horizontal velocity never changes. And so if it's launched at 70.7 meters per second, at any other time later in the problem, the velocity will still be 70.7 meters per second in the horizontal direction. That also means if we were to take the average velocity, well, the average of 70.7 and 70.7 is 70.7, and so we can write this also equal to V bar. This is going to happen every single time for a projectile problem. So it's a good idea to do it right from the start to remind yourself that no matter where you are in the problem, no matter when you are in the problem, the horizontal velocity will be 70.7 meters per second. And this takes the guesswork out. If just in case later on in the problem we need to know what the horizontal velocity is, we've already written it for ourselves. The last remaining piece of information is this 34 meters. Obviously, it's going to be a vertical displacement. It's falling straight down 34 meters. Although even though it's not moving straight down, that's the vertical displacement of 34 meters. So we're going to write delta y equals 34.0 meters. You can call it delta x if you'd like to, but if it's going vertically, I like to call that delta y to remind myself that's in the vertical direction. Notice I left the sign off of this. All right, so let's think about this. Should this 34 meters be positive or negative? So go ahead and put the sign on if you haven't already. It should be kind of obvious, I hope, right? It's clearly going down, and we call down the positive direction, so that's going to be a positive 34 meters. Okay, so now it's time for us to actually start solving the problem. So letter B asks, how long does the cannonball take to land? Again, if you have some experience doing this, you want to try to pause the video and try it on your own, that's great. If you want to follow along with me, also good. So our goal is to play around with some kinematics equations with the given information, working on one side or the other, and try to find how much time it's going to take to land. I will give you a little bit of hints in case you're not quite sure what to do. Maybe you want to start on the vertical side. Okay, so we know the initial velocity, we have the acceleration, and we have the displacement vertically. All we use the time. So we can do this in multiple steps, and there's nothing wrong with doing multiple steps, but it will be a little bit easier, a little bit more efficient if we use the displacement equation, delta y equals v naught t plus half at squared. Now, if you already paused the video and solved it, and you didn't use this equation, that's absolutely fine. There are other ways to do it. I'm just going to show you one way of doing it. As long as you get the same answer, it really doesn't matter. Now, this is one of the most important parts about projectile motion, which is really two-dimensional kinematics, that this dividing line right down the middle of the vertical and horizontal chart separates the information in either of the dimensions. And so if you're on the vertical side, you can only use vertical stuff, right? So on the vertical side, we look up here, we say, oh, we know what v naught is. It's 0, and anything times 0 is 0, so we can cross that off. But we can't use any of the horizontal stuff on the vertical side. It doesn't work that way. Okay, so what we want to do is we see we have delta y, we have acceleration, we want to solve this for time. So as always, we rearrange algebraically. And of course, when we rearrange algebraically, we get our usual shortcut equation, t equals the square root of 2 delta y over a. And in fact, if you jumped right to that, recognizing you're allowed to use it, that's absolutely fine. Now, how do we know we're allowed to use this shortcut? Well, we can only use this shortcut when initial velocity is 0, because that's how the algebra works out. And on the vertical side, initial velocity is 0. Could we use this shortcut equation on the horizontal side? No, the horizontal velocity initially is not 0, so this equation has no meaning. Okay, so at this point, go ahead and pause the video, put the numbers in, and find the time it takes for the cannonball to land. Okay, so put your numbers in, and you should get 2.63 seconds. It's obviously a 3 sig fig problem, so you have 3 sig figs in your answer. Now, I did box this in, but let's just consider this for a second, right? We're only on the vertical side. This basically says if you take an object, this cannonball, and drop it from rest to fall straight down 34 meters, it should take 2.63 seconds. That means the cannonball, if it were to just be dropped, not launched horizontally, should take 2.63 seconds to fall straight down to the ground. But that's not what it's doing. It's actually following this parabolic trajectory. So is this 2.63 seconds really our answer? It seems like it's only the vertical time. We want the whole time, so what do? Well, hopefully you recall the video that we watched in class. That was a very similar situation to this, where we had one ball that was launched horizontally to the side and one ball that fell straight down, and when they were launched together, we saw they fell the same vertical distance in the same amount of time. They hit the ground at the same time. And so this is the whole independence of motion idea, that the time to fall straight down is also the time to follow the parabolic trajectory, because the horizontal motion does not affect the vertical motion. And so yes, this 2.63 seconds is the time for it to hit the ground, even though it follows this parabolic trajectory, not falling straight down. All right, on to letter C. We want to find the cannonball's range. Okay, so range, that's a new vocabulary term. If you don't remember what that is, go back to the notes page and look it up. Of course, this is horizontal displacement. So obviously we're going to be on the horizontal side. So pause the video, pick your favorite kinematics equation, and go ahead and solve for its range. Here we have a couple of options. You could do delta x equals v naught t plus half at squared. There's nothing wrong with that. And really, that's the whole idea of independence, that even though we use this equation on the vertical side, we can independently use that same equation on the horizontal side as long as we stay on the horizontal side, right? We can only use horizontal stuff. And so I could look up here and I say, oh, I know the initial velocity, and I know the acceleration is 0. So what I'm not going to do is I'm not going to use the 9.8 meters per second squared, because that's on the wrong side. I can only use the 0 meters per second squared because it's on the horizontal side. And of course, anything times 0 is 0. Alternatively, of course, you can use my favorite equation, delta x equals v bar t. And you say, do we know what v bar is? Ah, yes, we do, because we already identified that v bar is the same as vf, is the same as v naught, because the horizontal velocity never changes, which is good, because we take a look at these two equations. One says delta x equals v naught t, the other says delta x equals v bar t. we should be able to use either one of those and get the same answer, and of course, v naught and v bar are the same thing. What time do we use? Well, we can use the 2.63 seconds because, again, that is the time for it to hit the ground. Time, being a scalar, is the one quantity that can jump from one side of the chart to the other. Everything else is a vector. It's got to stay on its side. So go ahead and pause the video, crunch your numbers, find the horizontal range. All right, you should have no trouble here getting 186 meters. Now, of course, there's one more kinematics equation that involves delta x. If you're not quite sure what it is, maybe you want to go look it up, go ahead and write it down. Of course, the time-independent kinematics equation, right? Vf squared equals v naught squared plus 2a delta x. Can we use this to find delta x? Well, remember, if we're on the horizontal side, we can only use horizontal stuff. And on the horizontal side, the acceleration is 0. And anything times 0, of course, is 0, right? Hopefully you see there's a bit of a problem with this. In fact, what does this really tell us? Well, once this whole term gets crossed off, it really says Vf squared equals V naught squared, taking the square root. That really all we've done is proven again that V naught and Vf are the same thing. Let's say you get a little confused though and say, oh, I'm just going to use this equation and rearrange it for delta x. What does that look like? Well, do the algebra. Just like we've done so many times before, of course, delta x equals Vf squared minus V naught squared over 2a. And once again, on the horizontal side, since the horizontal acceleration is 0, I think you can see what the problem is. And so basically, the time-independent kinematics equation just doesn't have any use on the horizontal side because the horizontal acceleration is 0. All right, let's go on to letter D. We want to find the cannonball's vertical speed as it hits the ground. So on the vertical side, pick your favorite kinematics equation. That'll get the speed. Pause the video, crunch your numbers. Again, we've got a couple choices here. We can do Vf equals V naught plus AT because we have the initial velocity at 0, we have the acceleration, and we just found the time. Alternatively, here we certainly can use the time-independent kinematics equation. In fact, maybe you prefer to do that because it doesn't even involve the time, right? Again, initial velocity is 0, we have the acceleration, and we have the delta y. So either way, no matter which way you go about it, you should be getting 25.8 meters per second. All right, now we go on to letter E, which asks to find the cannonball's total velocity. Well, didn't we just do that? Didn't we just find the 25.8 meters per second? Oh, wait a second. That's only the vertical speed. And remember, this is the challenge in two-dimensional kinematics. We have to remember at all times, the cannonball, the projectile, is moving both vertically and horizontally. So what do we have to do? We have to put together some components. We know as it's about to hit the ground, the vertical velocity is 25.8. What about the horizontal velocity? Oh, right. We wrote that Vf equals V naught. So horizontally, it's still moving at 70.7 meters per second. So let's go ahead and set up a vector diagram in the space by letter E. So here's our cannonball, and we're going to try to draw a vector somewhat to scale, right? So we have 70.7 horizontally and 25.8 vertically. And of course, I'm drawing 25.8 considerably shorter than 70.7. Now, the way I've drawn it here is not really right. They're tail to tail. We don't do that, right? We want to shift them so they're tail to head. So we shift this over. Normally, it doesn't matter if we do one first or the other first, but I will give you this advice. When we do these projectile problems, I absolutely want you to draw the horizontal velocity vector first and the vertical velocity vector second. And here's our tail to head connection. We're going to draw a resultant from tail to head, and of course, it's going to make sense, right? If it's moving to the right and down, we draw a resultant from tail to head. Look how it points to the right and down. As always, the resultant reflects reality. This resultant, of course, represents V total, and it does ask for direction as well. Which angle should we be finding, the upper left or the lower right? Well, I think you know, we always identify the angle near the beginning of the vector diagram, so there it is. And this is why I want you to draw the horizontal component first, the vertical component second, because when you do so, you set yourself up to find the angle to the horizontal, which is what we always do. So at this point, pause the video, do your Pythagorean theorem, do your inverse tangent, find magnitude and direction. Okay, you should be getting a speed of 75.3 meters per second and an angle of 20.0 degrees. All that remains is to describe that angle, and as we really emphasized in class, you're not going to refer to anything with north, south, east, west, because we're looking at it from the side, and south and down are just not the same thing. So hopefully you remember, how do we describe this angle? Right, we describe it as below horizontal. And so it boxes in our answer, magnitude and direction for the total velocity as the cannonball is about to hit the ground.